through our demos and some of the videos that we've seen, we discussed the fact that a projectile's motion is made up of separate components. The horizontal component on the x-axis, as well as the vertical component on the y-axis. And while an object has these two separate components at any one time, what's occurring in the y-axis has no effect on what's occurring in the x-axis, and vice versa. So these two axes are what we would call independent of one another. On the y-axis, or on the vertical axis, gravity is slowing down a ball that rises. But gravity only works by pulling something in that downward direction. So if a ball is thrown upward with a speed of 29.4, then after 1 second, it would have lost about 9.8 meters per second of its speed, leaving it to be traveling at about a rate of 19.6. After another second, it's lost some more of its speed. Now it's going at about 9.8. After another second, it's lost the last of its speed, meaning that in the vertical direction, it no longer has speed, or it's reached a speed of 0 at the top of its path. And then as that object starts to fall, then it will start to speed back up. Now gravity is working with the falling object, so it's going to accelerate it. So I'm going to go from 0, and about a second later, I've increased my speed by about 9.8 meters per second. But now it's falling in the downward direction. Another second later, it's increased its speed by again about 9.8 meters per second in the downward direction, so now it's going 19.6 meters per second. And another second later, it's increased its speed yet again. So now I'm going about 29.6 meters per second. So gravity is affecting the speed of my object in that vertical direction. It's also important to note that when my object was here at the base, I was going 29.4. At the exact same height, but in the negative direction, we're going that same speed. I apologize. 29.4 meters per second. At this height, I'm a little bit higher, so I've lost some of that speed. Our ball was going 19.6. At the exact same height, but in the negative direction, it's still going to be going 19.6. Again here, at this height, it's moving upward at a speed of 9.8. At the exact same height, it's now moving downward at 9.8. So the speeds are equivalent at a given height. Height determines the speed of an object has changed, the amount that an object has changed speed due to gravity. Now, in the horizontal direction, gravity is not pulling an object to the left or to the right. So that horizontal component is what we consider to be constant. It isn't being accelerated by gravity forward. It isn't being slowed down by air resistance pushing it backward. So there is nothing pushing forward on it. There is nothing pushing backward on it. So we have no net force. We have no acceleration. So if it starts out at 5 meters per second, and later it's going to be 5 meters per second. Another second later, still moving 5 meters per second. Even at the top of its path, when it's no longer rising and it's not yet falling, it's still moving at that 5 meters per second. As it starts to fall down, it's still moving forward. So every time it's moving in that forward direction. So even though our y component has changed to a negative, my x component remains exactly constant. So at that positive 5 meters per second in this case. Recognizing that an object has both vertical and horizontal motion, we need to figure out a way that we can combine those speeds together to produce one single motion that our eyes actually perceive. Because we obviously don't see something rising and then moving forward, and then see it rise a little bit and then move forward. This happens on a smooth rate. So that in-between rate is what we call a resultant. To calculate the resultant, we essentially use Pythagorean theorem. I'm going to use my a squared, my b squared, and calculate my c squared. or it can be written as x squared plus y squared equals our resultant squared. Obviously, we want the resultant by itself, so we're going to cancel out that square by square rooting our other two components. So let's practice that a bit. I'm going to clean up my page for a second. So if I wanted to calculate how fast that object was going at this instant up here, it's falling at a rate of -9 meters per second. It's moving forward at a rate of 5 meters per second. So if I do -9.8 meters per second squared plus 5 meters per second squared, and I take the square root of that, that's going to give me my resultant speed, which in this case, -9.8, that's going to cancel out. I get a speed of about 11 meters per second. Now it is moving in that negative direction. It is overall falling down. So I'm still going to give it that negative sign to show that we have a negative direction. 1 second later, I'm still moving at 5 meters per second squared. So that's my x component. And now my y component has gotten larger in the negative direction. So it's traveling at about 19.6 meters per second. So my a squared plus my b squared, or my x squared plus my y squared. In this case, if an object is falling at a rate of 19.6 meters per second, while moving forward at a rate of 5 meters per second, then its resultant speed would be roughly 20.2 meters per second. Because it's in the negative direction, we can give it that negative sign to show that negative velocity. Last one to try down here, I'm moving down at 29.4, so that's my y component. Moving forward at 5 meters per second, that's my x component, so x squared plus y squared. So at this point, it's moving down with a result of roughly 29.8 meters per second. In that downward direction, I'm going to put that negative component, that negative direction component on there. So next, we're going to take a look at exactly how we can figure out the different components of speed, time, distance, so how they relate to one another using some of our kinematic equations from our previous units. Again, it's important to recognize and note that our x and our y are horizontal, my horizontal and my vertical components are what we call independent of one another, meaning that just because one changes does not mean that the other has to change. So let's take a look at how our vertical motion can change. On the vertical component, gravity is going to play the largest role in what's affecting the speed of the object. So gravity causes the vertical speed to slow down or to increase at a rate of -9.8 meters per second squared. Recognizing that gravity is a cause and that gravity is an acceleration, then when it comes to doing calculations, the calculations that we are going to use are always going to include acceleration when dealing with that vertical component. Things that we want to remember from our previous unit as well from that previous page. When something reaches the top of its path, on the vertical side, it no longer has speed. It's no longer rising, and it hasn't quite yet started to fall. And again, gravity is the thing that's causing that object to slow down on the way up and to speed up on the way back down. So let's practice some calculations. If we wanted to determine the distance that an object had fallen in a set amount of time, then we would need to use an equation that includes our acceleration for gravity, as well as including a distance. And if I want to calculate that based on the number of seconds that something has fallen, then I would also need to include an equation with a time component. So my best equation of these ones above would be, well, this one doesn't have a distance, so that won't help me calculate how far something has fallen. This next one doesn't have a time component, so knowing how long that object has fallen wouldn't be useful to use that equation. My third equation has that distance component, our time, as well as our acceleration of gravity. So this is the equation that we are going to use in order to calculate how far something falls in a set amount of time. If I wanted to do it for 1 second, 2 seconds, 3 seconds, 4 seconds, so we'll get some general practice. So my displacement is going to be my initial velocity. If something is falling, then obviously its initial velocity up at the very, very top, the highest point, is going to be 0. So I would use 0 times my first second plus half, which is part of the equation, times gravity, and then my time again, and squared. Simply plug this into the calculator, let the calculator do the work, and my object will fall negative direction by about 4.9 meters in that first second. Now, most of us pretty quickly start to recognize that when something is falling, we can simplify this equation by canceling out that beginning part. So if we are the displacement from rest can be simplified to be 1/2 times our gravity, its acceleration, times the time squared. So if I want to know how far that object's going to fall after 2 seconds, I'd simply use half times that acceleration of gravity, and then my time and squared. So half of 9.8 is 4.9, and 2 squared, and I can solve using my calculator. So after 2 seconds, I would have fallen negative direction by about 19.6 meters. Go ahead and try to set up the third and the fourth seconds of falling as some extra practice on your own. Take a minute and try. If you've done your math correctly, then after 3 seconds, we've fallen roughly 44.1 meters. And after 4 seconds, we've fallen about 78.4 meters. Next, we're going to look at how we could calculate the velocity of an object that falls because of gravity, again, in a set amount of time. So to do this, we're going to use that velocity, which we'll see in our first and our second equation, but not in our last one, as well as our gravity, which we have in both equations, but only the first one also includes time. So that's the one that we're going to use, because for this set of examples, we don't care about how far the object has fallen in each of those seconds. So to calculate this, our final velocity is going to be equal to our initial velocity. We're resting, we're starting from that highest point, plus the acceleration of gravity times the number of seconds that we've fallen. And again, pretty quickly you'll recognize that we can start to cancel out certain parts if we're falling from rest. So after 1 second, I've fallen and reached a speed of about 9.8 meters per second squared, making it negative because, again, that's negative direction. After 2 seconds, again, 0 is my initial, my acceleration is due to gravity, and now I'm falling for 2 seconds. So negative 9.8 times 2 After 2 seconds, our object will have a speed of roughly 19.6 meters per second. Go ahead and take a second, try the third and fourth second on your own to see how fast something will go after falling for 3 seconds and after falling for 4 seconds. So if you've done the math correctly, we're going to see that our velocity after 3 seconds should be roughly 29.4 meters per second in the negative direction. And after 4 seconds, that object is going to be traveling at about negative 39.2 meters per second. Again, negative implies a downward direction or a negative direction. So we've seen that how we can use our equations to calculate the distance that something falls, as well as the speed that it reaches in a set amount of time because of gravity. Next, we want to look at when gravity doesn't have an effect. So gravity pulls objects down. Gravity does not pull objects left and right. Meaning that if gravity is trying to accelerate things in that downward direction, and there is nothing accelerating them in the left or right direction, then the velocity must be constant in that left and right, that horizontal direction. So the only equation we have that does not include acceleration is our very first equation we learned this year, where the velocity was equal to the distance divided by the time. We have written on our notes here a rearranged version where we can see that we've cross-multiplied the velocity and the time, and that can be very helpful in calculating the distance that something travels. So let's see what happens. Determine the horizontal velocity of a ball that travels 7.5 meters each second. So 7.5 meters, that would be my distance. Each second, so every 1 second, that object is going to travel roughly 7.5 meters. So the velocity of my object would be 7.5 divided by 1, or 7.5 meters per second. So if I travel 7.5 meters each second, then if my velocity remains 7.5, and I assume that I let that object go for 2 seconds, then after 2 seconds, my object would travel roughly 15 meters. If I let my object traveling at 7.5 meters per second go for 3 seconds, then I can see that my object would travel about 22.5 meters. So when we're calculating the velocity or the time that something falls or the distance that something falls, where it's falling in that vertical direction, we need to include gravity. In the horizontal direction, we do not include gravity, and so we use only equations that do not have that acceleration component in them. So our initial equation for finding velocity, or our rearranged equation here for if I want to know how far something's traveled. So now let's put it all together. When something travels with both horizontal and vertical speed, we call that a projectile. So a projectile is anything that combines that x component and that y component. As an object goes up, we're going to see that that vertical component starts to get less and less and less until eventually it stops at the top, whereas our horizontal component continues to be the same. In doing so, if we were to mark those points on a graph and connect the lines, we would always end up with a parabola or a curve. So the general shape of a parabola is made because we have a consistent horizontal speed whereas vertically, we have a large change here, and then less of a change here, no change here, smaller change, and again back to a large change. So we have that y component changing a lot very quickly. If I were to shoot something straight up into the air, all of its energy would be directed up, meaning that it would have the maximum vertical distance, go as high as it possibly could, but it would have very little or no horizontal distance. Similarly, if I shot something straight to the side and used all of that energy to go forward, it would have very little energy to go up or down and would quickly fall. Okay, it would maintain that height, So if I want something to travel both high and far, a 45-degree angle gives me a maximum horizontal distance. So that maximum horizontal distance is going to come because I'm not wasting all of my energy in the vertical direction, and I'm also not wasting all of my energy in the totally horizontal direction either. I've got kind of the median or the best of both worlds. One of the important factors that we're going to find when trying to do calculations or determine information about an object's motion when it has both components is time. Time is consistent regardless of whether I'm moving forward or up. So if I know the time that it takes for something to fall, I also know how long that object is going to fly forward. So being able to calculate the time that it takes for something to move is going to become very useful to being able to compare and understand how that vertical motion can affect my horizontal motion and vice versa. As we saw in one of our previous worksheets was when we want to put these speeds together, we call that the resultant velocity. And so here we've got that reminder of what equation we can use in order to calculate these different components. So the last thing that we're going to do here is we're going to look at exactly how those numbers that we calculated earlier relate to an object's motion. So up here we have a scale where 1 centimeter is about 5 meters, shrinking that information that we calculated down to something that was workable. So this first dot that we have on top shows that an object has gone about 7.5 meters in 1 second, and 7.5 more meters in 2 seconds, 7.5 more meters 3 seconds, 7.5 more meters in 4 seconds. These dots up top are equally spaced because we have that constant motion. We're also going to plot out the points that we calculated earlier regarding the distance that something falls in a set amount of time. So we said that after 1 second, an object had fallen about 4.9 meters. Let's call that 5. So at 1 centimeter, I can put a little dot to show that it's fallen that distance. After 2 seconds, we said that it had fallen about 19.6 meters. So let's round that to 20. 5, 10, 15, 20. So I'm going to put a little dot to show that it reached about 20. Next, we said that after 3 seconds, it had fallen about 44.1. So 44, 45. Let's try that. 5, 10, 15, 20, 25, 30, 35, 40, 45. And then after 4 seconds, we said that it had fallen 79 or 78 meters per second. So let's call it about 80. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. So we're just above the ground at that 79 meter mark. So we see that the distance between our dots has started to increase. This shows that our object has accelerated as it falls. If we were to try to plot out where this vertical motion were to meet our horizontal motion, then we can determine the location of our object at a given set of time intervals. So, after 1 second, our object would physically be located here, where it's moved forward some because of the horizontal motion, and down some. After 2 seconds, it'd be located here, 3 seconds here, 4 seconds here. If I connect my dots, then when I throw that ball and it starts to fall, I end up with that downward displacement curve that we've practiced with, which again we would call part of a parabola or a parabolic curve, showing that exponential change in the y direction.